Hello, this is Professor Brown-Cedarberg, and I'd like to spend some time talking about BigONotation. Now, BigONotation is a way to communicate the time or the memory it takes for an algorithm to complete its execution on a data set. So it's a measure of how fast an algorithm will run, how much memory it'll take. We're going to concentrate on the time. So what really it does is it tells us the efficiency of our algorithm. The efficiency of our algorithm as the data set on which that algorithms operate as it increases. So how does that algorithm respond to changes in the input size? It's really how does our algorithm scale? Now, BigONotation, we remember, refers to order of, and it's always dealing with the worst case scenario, and it really relates to the complexity of our algorithm. Now, when we talk about BigONotation, we're going to use n, and n is simply the number of items in the data set. It's the number of things that our algorithm has to work with. So, BigONotation communicates complexity, or it's related to complexity. And here we've got a chart, and it shows on the left-hand side how we communicate that complexity, or really the amount of time, the amount of space that our algorithm requires. Right? And you'll see that's O of 1, O log n, O n, etc., etc. Middle column is a listing of the number of operations if I have 10 elements in my data set. Right-hand column, the number of operations if I have 1,000 elements in my data set. And you'll see that with this chart, BigONotation, it really tells us how our algorithm, the number of steps, the number of operations that have to be taken, how it changes as our data set increases. So in the first row, we've got O of 1. That's constant time. And so in O of 1, if an algorithm is O of 1, it takes one operation for 10 elements. It takes one element for 1,000 elements. It takes one operation for 1,000,000 elements. It's constant time. We're going to come back to this chart. We're also going to look at that chart in graphic form, and here it is. We'll come back to these both several times. All right, now if we're talking about BigONotation, we have to understand a logarithm. And the definition of a logarithm requires us to work with three numbers, y, x, and b. That's how we're going to note them. So the log y, that's the number we're looking for, of a number x is the exponent another value, that's the base, we'll call that b, must be raised to produce that number. So here I've got y, that's the number I'm looking for. That number is the number by which b, the base, has to be raised to produce x. So if I am looking for log 10 1,000, my answer is 3, because 10 has to be raised to the third to produce 1,000. 10 times 10 times 10. If I'm looking for log 2 16, my answer is 4, because 2 has to be raised to the fourth to produce 16. 2 times 2 times 2 times 2. That's a logarithm. All right, so let's look at this. This is O of 1, constant time. We've looked at this a little bit. So I have the same amount of time, same number of operations, no matter what the size of n. So if I have 10 elements, one operation, 1,000 elements, still one operation. If I look on the chart, I know that it's O of 1 and I should see a blue line, but I don't see a blue line on my chart. I don't see my blue line because pretty much O of 1 is a dot. I'm going to constant time, same number of operations, no matter what the data set. And you see on this chart, I've got the number of elements is the x-axis, the number of operations is the y. So let's look at O log n. O log n is known as logarithmic time. It's greatest at the beginning, then it flattens out. As n increases, right, it takes longer, but the increases get smaller and smaller and smaller. The amount of change decreases. So with O log n, if I have 10 elements, I've got 3 operations, 1,000 elements, 7. My chart would look like this. I'm looking for this red line. You'll see that it's pretty much looks flat. It starts out really at its greatest, and then the amount of increase decreases and decreases and decreases. The amount of time doesn't, but the amount of change decreases. So it pretty much looks like a flat line. And then I move on to O of n. This is linear time. The growth is directly proportional to the size of n. So in O of n, if I have 10 elements, 10 operations, 1,000 elements, 100 operations. We see that here in our line here. So we move on to O n log n. This is log linear time. And what happens here is I do O log n operations for each item in the input. So if n is doubled, I take a little more than twice as much time. So with O n log n, if I have 10 elements, 30 operations, 1,000 elements, 700. And if I look on the chart, that's my purple line, and you see it right here. So there's a bit of increase. Moving on, we look at O n raised to the second, or n squared. And this is quadratic time. Every element requires that you do something with every other element. So if I have n double, then it takes 4 times as much time. On my chart, O n raised to the second, or n squared, if I have 10 elements, it's 100 operations. 1,000 elements, 10,000 operations. My chart looks like this. Pretty steep increase. I then move on to O2 raised to the n. This is exponential time. And the time required in this will double with each element that I add to the data set. And so with O2 raised to the n, if I have 10 elements, I'll have 1,024 operations. If I have 1,000 elements, I'll have 2 raised to the 100. If we look at my chart here, we'll see that I have almost straight up growth. Lastly, we'll look at O n factorial. This is called factorial time. And it processes all the possible permutations. And a permutation is an arrangement of items in a specific order. Okay? It processes all the possible permutations of the elements. And it has very fast growth. O n factorial, if I have 10 elements, I've got a large number of operations. But my operations for 1,000 elements is more than huge, 100 factorial. And if I look here on my chart, O factorial, you'll see that it's pretty much a straight up line, that we have that much growth in the number of steps we have to take. So this quick examination of BigONotation, okay, we know that BigONotation measures the efficiency of an algorithm, communicates that. That efficiency, as the data set it operates increases, okay? And it really is how an algorithm responds to changes in the input size. We looked at the different notations for big O: O of 1, O log n, O of n, O n log n, O n squared, O2 raised to the n, and O n factorial. This has been a quick tour through BigONotation. I encourage you to do more research. It's a fascinating subject and one that will help you as you develop more complex algorithms. Thank you.